The term energy is used in an unconventional sense here. We are instead using the word energy to give the size of the signal. In order to measure the energy of a signal, we must take into consideration its length and amplitude. To easily do this, we can take the integral, or area, of the signal to give both its length and amplitude in one number. Therefore, can we define the energy of a signal as just its integral over the bounds on which it exists? Let's do an example. We have a signal defined by the function f of t equals t, where t exists from -5 to 5. If we take the integral of this function, you will see that we get some cancellation, since this function is symmetric about the y-axis. So taking our function t from -5 to 5, it integrates to t squared over 2, which becomes 25 over 2 minus 25 over 2, which equals 0. But if we have a real signal defined by this function, the energy cannot be 0. It exists, it's real, and must contain some energy in order to exist. For example, think of light as a sinusoidal wave, or function, or signal, propagating through space. If we calculate the energy of part of this wave function and find that mathematically it has 0 energy because of some cancellation by taking the integral, then does this mean that the light wave has 0 energy? Of course not. Therefore, to counter this cancellation, we can square the function representing our signal, in this case f of t, equals t, then take the integral of this squared function. If we graph this function, t squared, we'll get a parabola going from -5 to 5. Then if we integrate t squared from -5 to 5, we get t cubed over 3, which equates to 250 over 3, which is a non-zero value. Finally, we can define the energy of a function as a function squared from -infinity to infinity. Let's do one last example to illustrate this equation. Say we have a function f of t, which is 5t plus 1, where t exists from -5 to 0, and e to the t, where t exists from 0 to 2. We'll call this one example 2. So the energy of f of t is equal to the integral from -infinity to infinity of f squared of t dt, which equals the integral from -5 to 0 of our first function 5t plus 1 squared, plus the integral from 0 to 2 of our second function e to the t squared, which equals, after you expand it and integrate it, 25t cubed over 3 plus 10t squared over 2 plus t, taking that from -5 to 0, plus e to the 2t over 2, taken from 0 to 2. After substitution, the first quantity comes out to 922, plus our second quantity, which comes out to approximately 27, which equals a total of 949. And we're going to use units of, since this is technically the area, we're going to have units of our y-axis by units of our x-axis. So typically the x-axis is going to be in seconds, and our y is going to be some sort of amplitude. For example, we can say that our y-axis has units of volts, since we're measuring the voltage. So in this case, it will be 949 volt seconds. So far, we've been doing examples of real signals, but what if you have an imaginary signal, or a signal represented by a function that contains I or j? Calculating the energy will follow the exact same format and formula, but we will take the magnitude of the function before squaring it, illustrated by the following formula. If you'd like to download all of these notes that I've been taking throughout this video, I'll make it downloadable in PDF form in the description of the video below.